The term wave-particle duality refers to the fact that the behavior of light can sometimes be explained by thinking of it as a wave, but sometimes the only way you can explain it is by thinking of it as a stream of particles. So we say light has a dual nature. It's either a wave or a particle depending on the phenomenon being observed. Now, in the 1920s, de Broglie suggested that wave-particle duality probably applies also to particles, not just light. So particles, little particles like electrons, he said, might have a wavelength associated with them. So he came up with a formula. The wavelength of a particle in this formula is just equal to h being Planck's constant, divided by p, where p is the momentum. Momentum is just the product of the mass times the speed of a particle. Okay? And de Broglie's hypothesis was eventually confirmed by experiments performed by Davison and Germer. And Davison and Germer were able to demonstrate that electrons, okay, which we normally think of as particles, exhibit diffraction. Okay? Diffraction, as we've seen earlier, is a characteristic of waves. In fact, this is the basis for using electrons in microscopes. So you've heard of electron microscopes. Okay, so a beam of electrons can behave just like a beam of light. All right, so here's an example. Let's calculate the de Broglie wavelength. If you have a 1 kilogram object, let's say moving at 1 meter per second, what would be its de Broglie wavelength? So let's apply de Broglie's formula. Lambda is h over p. H is Planck's constant, 6.626 times 10 to the negative 34 joules times seconds, divided by our momentum is mass, which is 1.00 kilogram, and our velocity, our speed is 1.00 meters per second. Okay, so let's look at our units here. Okay, a joule is a kilogram meter squared per second squared. All right. Remember, a joule is a unit of mass times a squared unit of speed. Okay, so if you recall, energy is 1/2 mv squared. So a unit of mass times a unit of speed squared. So unit of mass times a unit of speed squared. That's one way of thinking of joules. Okay, so let's see what happens to our units here. Kilogram cancels out. Okay, one of the meters will cancel out with this meter right here. I have second to the negative 2 times second, that's second to the negative 1. That's per second in the numerator, and you have per second in the denominator. That also cancels out. So this just leaves meters as the unit. So let's calculate that. 6.626 times 10 to the negative 34 divided by 1 divided by 1. Now, it's kind of easy. 6.626 times 10 to the negative 34 meters. Now, one thing that's striking about this number is this. It's a very, very small number. 10 to the negative 34 meters. Okay, that's way smaller than the diameter of the nucleus, which is somewhere between 10 to the negative 13 and 10 to the negative 14 meters. So what that means is the wave-like behavior of a 1 kilogram object moving at 1 meter per second would be imperceptible. It's not detectable because the wavelength is so small. Okay, so you don't worry about wave-like behavior for what we would call macroscopic objects like a 1 kilogram object. But the wave-like behavior becomes important once you're dealing with small particles like electrons. Okay, because the small particle would have a small mass. So down here, your momentum is going to be small. And that could make your lambda big enough to be detectable, as illustrated in this next example right here. Let's say you have an electron with a mass, which has a mass of 9.11 times 10 to the negative 31 kilograms, moving at a speed of 10 to the 6 meters per second. Really fast speed. Okay. So let's calculate our de Broglie wavelength here. Lambda is equal to h over p. Okay, so h is 6.626 times 10 to the negative 34 joules times seconds, divided by our momentum, which is mass times speed, so 9.11 times 10 to the negative 31 kilograms, and our speed is 1.00 times 10 to the 6 meters per second. Okay, and that gives us, if you do the calculation, I have the answer here already, that's 7.27 times 10 to the negative 10 meters. So that's 7.27 angstroms, or 0.727 nanometers. Okay? What's interesting about this result is that, okay, the typical distance between atoms in a solid or in a molecule will be 1 to 2 angstroms. And 7 angstroms is comparable to that. Okay? And so, because that wavelength for these electrons is comparable to the distance between the atoms, it's comparable to the barrier distance between the barriers that they will encounter if they were to encounter a solid, okay, then you would expect to see a diffraction pattern coming from the electrons when it encounters a solid.